So we've been talking about diffusivities and random walks, and particularly diffusion in the gas phase. And we talked last time about the kinetic theory of gases and the predictions that it makes about gas phase diffusivities. And then we got to this Chapman-Enskog formula. And let me just recap the final results from that. Remember that the Chapman-Enskog formula took account of the interactions between molecules in the gas phase, and they stick together in pure gases. They stick together with these parameters epsilon AA. It characterizes the sort of binding affinity between these gas phase molecules, and we can get these parameters epsilon AA from the equations of state for different gases, small molecule gases, and then we can blend them, or we can mix the parameters for the individual molecules sticking to themselves to get estimates for how strongly pairs of molecules will stick to each other, unlike molecules will stick to other kinds of molecules. And so that's a pairwise binding affinity parameter. And there's also a parameter that describes the effective diameter for the collision pair that involves a molecule of type A and a molecule of type B. So you've got here a geometric mean gives you the binding affinity parameter, and a arithmetic mean gives you the diameter parameter, and a harmonic mean of the two masses gives you the effective mass for the collision pair. And so these parameters all enter into the Chapman-Enskog formula for the diffusivity, which gives this expression here. I won't read it, but the important things are that temperature scales as T to the 3/2, effective mass to the -1/2, pressure to the 1/2, or pressure to the -1, the diameter of the collision pair to the -2. And there's this other term in here. This is this collision integral. The omega here is a term that depends on the binding affinity relative to kT. And so some charts will give you this parameter as epsilon over kT, and the one here gives you this parameter omega as a function of kT over epsilon. Okay, so make sure you're looking at the right kind of chart so that you don't read off 1/2 when the real binding affinity in kT units was 2, for example. Okay, so keep that in mind. This is basically the numbers tabulated in Kussler's book. And so what you see here is that when the molecules stick together very strongly relative to kT, you have a very big collision integral. When they stick together very weakly relative to kT, so here epsilon is becoming very small compared to the thermal energy, and that gives you a very large value of kT over epsilon, then that collision integral drops down, becomes very, very small. Okay, so it's particularly useful in problems like this to put in some typical values of these different numbers, the temperature and the effective mass and the pressure and the diameter and the collision integral, and get a characteristic value for the diffusivity, and then you can use the scaling relations that are implied by the dependence on all these different properties to quickly and easily calculate the value relevant for the problem at hand. Okay, so the Chapman-Enskog diffusivity at a pressure of 1 atmosphere at temperature 300 Kelvin, when the collision diameter is 1 angstrom, that's really small, and when the effective mass is 1 AMU, that's also very small, and when the collision integral is 1.0, gives you a diffusivity from the Chapman-Enskog theory of 14.1 times 10 to the -4 meters squared per second. Okay, so now you can take this value and you can scale it according to the dependencies on temperature, pressure, diameter, and mass accordingly. Okay, so an alternative approach is to actually build in numerical values for all of these different terms. That's what Kussler has done, and he gives you 1.86 times 10 to the -3, sort of no explanation for where that number comes from. It's important to remember that that number then depends on what units you've used to compute your diffusivity. It is a value in centimeters squared per second. So be careful there. You want to change to 10 to the -7 if you're doing if you're reporting diffusivities in meters squared per second, and then you actually plug in the values of all the temperature and mass and pressure and all those things. Have to be careful that you use the same conventions on what units you use for the mass, what units you use for the pressure, what units you used for the for the diameter, right? So this is sort of the disadvantage of reporting things this way, but it's common in engineering to do so, and you have to get used to it. So you want to pay attention to this example and make sure that you know what kinds of units go in to use this formula in Kussler's book. Okay, so here's an example. We can go to the tables and look up properties of argon and hydrogen at 1 atmosphere and 175 degrees C. So the relevant properties are the diameter of argon, that's 3.54 angstroms. Diameter of hydrogen is given here. You add these two, divide by 2, you get an effective diameter of 3.18 angstroms. So another parameter that goes into the Chapman-Enskog theory is this binding affinity in units of temperature. This is the epsilon for argon over Kb is 93 Kelvin, and for hydrogen it comes up to be 60 Kelvin, so the geometric mean of those two is 74.7 Kelvin. The effective mass, the atomic mass of argon, 39.9 AMU. For hydrogen, it's 2.02 AMU. Those masses will go in here, into this thing, right? And we have to divide, we have to scale that effective mass by 1 over 1 plus 1 over 1. Remember that the mass of A and the mass of B were the values that I use in computing this reference diffusion constant. So from the epsilon value and from the temperature now, we can get epsilon for the pair argon and H2 over Kt is 0.167. Okay, so now going back up to the chart, we can look and see where does that place us. Okay, so we've got epsilon over kBt. Now be careful, that actually corresponds to a Kt over epsilon of about 6, which should be somewhere in the neighborhood of here. Looks like about 0.81 or so, and that's where this value came from. So the omega of 0.81 came from inverting this to get Kt over epsilon and then reading it off of that chart. Okay, so there's my value of omega. There was a 1 there before, so we don't really have to scale that one. This was my diameter squared, was also a 1, so we can just put in the new number down there. Here was the original reference diffusivity in meters squared per second. There is the new temperature divided by the actual temperature. The dependence on temperature is to the 3/2 power, so we just take that ratio to the power 3/2. Here are the two reduced masses, the reference and the actual to the power 1/2. And at the end of the day, you get 1.6 times 10 to the minus 4 meters squared per second. The experimental value is 1.76 times 10 to the minus 4 meters squared per second. Now, this is really remarkable for a theory that has no adjustable parameters, right? I mean, the only thing that we are using here are actual properties of the argon and the H2, right? So it's really quite amazing. I hope you share my enthusiasm. That this theory is able to do so well at predicting the absolute value of this diffusivity. Quite a landmark achievement in statistical mechanics. Okay, so it's true though that these sigma and epsilon parameters are not always available. Certainly, they're not. Kussler only lists maybe tens of compounds, so there's a lot more stuff out there. And often we don't have its properties and don't have time to go through and measure it. And so the question is there an easy way to get a crude estimate on the diffusivity when you don't know anything about the properties of the compound that you're working with? Well, that's what the Fuller correlation is for. You can estimate the effective collision diameter by looking at the sum of the atomic volumes of all the constituents in species A. You add all those up, you take it to the 1/3, that gives you a length, right? So that you can think of as being the effective sigma A for molecule A, which is comprised of all of its individual component atoms. And you also get a volume for molecule B by adding up all of its constituent atoms. Take that to the 1/3, and that gives you a diameter for component B. You add those two together, just like you do in the Chapman-Enskog formula, and then you divide it by 2. That constant 2 has been absorbed into here, and then you square it, right? So this part looks just like Chapman-Enskog. Likewise, the dependence on the molecular weights looks the same as in the Chapman-Enskog theory, and the dependence on pressure is the same as in the Chapman-Enskog theory. Again, this is a correlation, so we have to say what kinds of units we're going to put into these things. Pressure is in atmospheres. These diameters are going to be in angstroms. The masses are going to be in atomic mass units, and the temperature always in Kelvin. And this numerical value then sitting in front will give you the diffusivity in meters squared per second. So, you know, these sums of these structural volume elements of the individual atoms in a compound, those are kind of hard to get. They are not tabulated in Kussler, which is kind of unfortunate. Kussler, if you make a 4th edition, please put those in. You give this formula and then don't give us the values that we need to use it. But Jean Koplis has these things tabulated for many of the common atoms that you might occur in a compound, and so then you can go through and you can actually use this for compounds that you've never seen before. It works pretty well. So you'll notice a slight difference here. The temperature is now to the power 1.75. That's accounting for the fact that in that collision parameter there was effectively a dependence on temperature. As you change the temperature, the ratio of epsilon over Kt is changing, and that's changing the collision parameter, and that gives you effectively a little bit of an extra 0.25 power dependence on the temperature. So that's sort of built into the Fuller correlation empirically, and we don't need that collision parameter anymore. So if we go through an example using the Fuller correlation, this one takes N-butanol in air at 1 atmosphere and 0 degrees C. So he obtains 7.73 times 10 to the minus 6 meters squared per second. And that's pretty slow for the gas phase. That's because N-butanol is a large molecule. Now if you were to go through and compute the diffusivity at a different temperature, you could just scale by the prediction of the Fuller correlation, right? So you'd have 299 over 273. There's your 25.9 degrees C over 0 degrees C value in kelvins to raise to the power 1.75, and that gives you the new diffusivity. And if you were to want to double the pressure, say, and ask what will that do to the diffusivity, well, it will cut it in half, right? So you get that by looking at the dependence of the diffusivity on the pressure, and that just cuts the diffusivity in half from this previous result that we computed. So these scaling rules are quite useful, and these correlations are quite powerful. I encourage you to learn how to use them for the exam. So our next session will be about diffusivity in liquids. Today is all about diffusivities. We're going to talk about the molecular basis for these properties, and you know, before really getting into the molecular details of how diffusion works, let's just say a little bit about the general sort of mathematical features of random walks. So diffusion basically is a random walk. It is a random walk, if you want, you can think of as this meandering trajectory taking little steps in all directions with no bias for any one direction that looks something like this little trajectory shown here. So it starts right here at the origin in this coordinate system here showing two-dimensional random walk, and after some time, even though the trajectory isn't biased to go in any one direction, it does move away from where it began, right? So you may find it over here, you may find it over there, but you will find it somewhere off away from displaced from where the trajectory started. And so this is after some time, delta t, and the theory of diffusion predicts that this mean squared displacement behaves like 2 times the diffusivity times time in 1 dimension, 4 times the diffusivity times time in 2 dimensions, and 6 times the diffusivity times time in 3 dimensions. Okay, so let's kind of get an idea for why the formula looks like this by considering a random walk in a single dimension. Okay, so imagine that at every single time step, delta t, this random walker takes a step plus or minus a small distance L along this x-axis. So x here is the vertical direction and time is the horizontal direction. And so we're going to take random steps up or down, and we're starting out at the origin. And so, you know, each of our steps are of size plus or minus L, and the total distance that we've moved from the origin here is the sum of all those steps, right? So what is the position after n steps? Well, it's just the position after n minus 1 steps plus a random plus or minus L from the nth step. And so we can ask now, what are the statistics that describe the variance or the width of this distribution? And so that is given by the mean squared size of this xn, which can be expanded, right? I can use this formula and square the right-hand side now, and I get xn minus 1 squared. I get a cross term that involves xn minus 1 and the random step, and I get the random step squared. Now, this term is obviously going to also be positive, and this term is clearly L squared. But this term is a random displacement times another random displacement, and there's no correlation between the n minus 1 steps that happened before and the nth step. And so because of that, these things being independent, this cross correlation term here just vanishes from the average, and you end up with this identity that xn squared is equal to xn minus 1 squared plus L squared, which is really pretty important. It tells you that that the squared displacement after n steps is is growing by L squared with every single step. Okay, so each step now contributing the same amount to the variance tells you that you must have that the mean squared displacement is proportional to the number of steps times the L squared because of the way this formula grows. Okay, so now how many steps did we actually take? Well, that's the number of steps is the total time elapsed divided by the time interval per step. And therefore, we can write down this formula that tells us that xn squared is equal to 2 times this result, L squared over 2 delta t times t. And so we identify this quantity in parentheses as our diffusivity in one dimension, right? So if the steps are L squared and the time interval between steps is delta t, then we would write down the diffusivity as L squared over 2 delta t. Okay, so that's a pretty useful estimate to remember that you can get an order of magnitude on what is the diffusivity by thinking about the size of steps and the frequency with which they occur, and taking a ratio of those two things in this manner. Okay, so the key results now are that the mean squared displacement as a function of time is proportional to time and to the diffusivity with this factor of 2, and that of course means that we've defined diffusivity as L squared over 2 delta t. Okay, so that is a little introduction to the way diffusivities work. Of course, the size of those steps and the frequency with which velocities are randomly changed depends on the medium that you're in. And so that brings us to thinking about diffusion in gas phase, diffusion in the liquid phase, and later we'll talk about diffusion in solids. For now, let's just think about the kinetic theory of gases, where you have gas molecules described as, in the simplest case, just hard spheres. And these are at low concentrations, so we can ignore the three-body collisions that would happen occasionally, and instead think only about these binary collisions, right? So you can think of a bunch of billiard balls, a dilute gas of billiard balls flying through space, and they're bouncing off of each other. And these are our molecules, and every time they collide, their velocities are randomized by that collision, and that results in the random changes in direction that occur at a direction of motion that occur at intervals delta t, which is the time between collisions, if you want. Okay, so people have thought very carefully about this and worked out a lot of beautiful statistical mechanical theories and shown that the flux of a species A in these gas molecules, this is sort of a self-diffusion result actually, is minus 1/3 of the root mean square velocity multiplied by the mean free path between collisions, right? So this is something you may have learned in your PChem class, that you can work out what is the typical distance traveled between collisions between these billiard ball gas molecules, and you can also work out from equilibrium statistical mechanics what is their root mean square velocity. And then you multiply this by the gradient of the concentration of a particular species that you're considering, and that gives you the diffusivity, the flux, the diffusion flux of that species. So from this expression now, and just looking back at Fick's law, we can identify that the diffusion constant for hard spheres in the kinetic theory of gases must be this expression, 1/3 of the root mean squared velocity multiplied by the mean free path. Okay, so that's the result that comes out of pure component vapor. Okay, you know, a little detail on what these characters are. The root mean square velocity from equal partition is easy to remember because you're just saying that the average kinetic energy, which is 1/2 of m average v squared, is equal to kBt. That's the thermal energy, right? So these things your science teachers told you in elementary school about temperature being related to kinetic energy were actually true. And so this is the formula from equal partition that gives you this root mean squared velocity. So, you know, solving for VRMS, just, you know, take the square root of the right-hand side and you've got that. What about the mean free path? That's a little bit more difficult to derive, but you can imagine how the calculation would go. You think about the cross-sectional area of the particle, and the rate at which it's traveling is this mean squared velocity, and as it moves through space, there can be nothing in this little cylinder that it traces out, or it's going to have a collision. And so based on the density of these particles in space, which is given by the pressure and the temperature, you can estimate how frequently it will encounter another particle and have a collision, right? So basically the argument is that the average volume swept along this cylinder between collisions must be equal to the volume per sphere in the gas phase, and that gives you an expression for the mean free path. You get pi/4 times sigma squared. Sigma is the diameter of these particles, so that's their cross-sectional area, and this is the kT over P. When you see kBt in this class, remember that is just the gas constant, okay? So the only difference between them is this unit conversion of going from molecules to moles. So this is Boltzmann's constant, but it's really the same thing as the RT that you've learned to use as your gas constant. All right, so that's the kinetic theory of gases result. When you combine these two things, you can see in gory detail how the diffusivity from the kinetic theory of gases depends on temperature, on the size of the molecules, on the pressure, and on the molecular weights of those molecules, right? So you have predictions now that come from the kinetic theory of gases. They're not bad, actually. So the T to the 3/2 is pretty close to being correct. M to the 1/2, N to the -1/2 is correct. P to the -1 is correct. And sigma to the -2 is correct. Okay, so kinetic theory of gases, this very simple framework, does a pretty good job. And so this alone will maybe not allow us to do a good job predicting absolute diffusivities, but certainly is good enough to predict how diffusivity will scale when I make a change in temperature, when I make a change in the mass, when I make a change in the pressure, etc. So, you know, it took a bit more effort to work out the diffusivity in the case when you have two-component gas mixtures. So there, you know, things are roughly similar, but now you have an effective size that is the arithmetic mean of the two sizes of the constituent of the mixture. So you've got A and B, their diameters, you add them, you divide that by 2, and you also see that you get this harmonic mean for their masses entered instead of the mass of either one of them. Okay, so this is basically standing in for a effective mass of the A and B collision pair. And you also see that the temperature and the pressure dependence are exactly the same. There's a little bit of a change in the prefactor here. So this is the result if you have a two-component gas mixture. Again, you know, the real value of this kinetic theory of gases is in predicting the scaling of the temperature dependence and the pressure dependence and size dependence and mass dependence. And all those things were really there in the single component gas. But you could use this to predict diffusivities, but it's not extremely accurate. A more accurate theory is that of Chapman-Enskog, quite a celebrated result in non-equilibrium statistical mechanics, thinking about, for the first time, how the degree to which molecules stick to each other and have you know, partially inelastic collisions then will affect the the diffusivity of those molecules. So you can imagine that, as molecules collide, if they stick for a moment, then during that time when they're stuck, there are, excitations that have happened in their internal degrees of freedom, and the collision pair is traveling more slowly, and then maybe they transfer that energy back from their internal degrees of freedom into the separate degrees of freedom for the kinetic energy of those two particles, and they separate then. But this process, sticking during these collisions, actually affects the diffusivity, can affect the diffusivity quite a bit. So, thinking about this molecularly, there is an interaction potential between all molecules. Even things like argon have a little bit of an interaction potential between each other, and so you have potential energy here on the vertical axis and distance between the two molecules involved in the collision on the horizontal axis, and there's a repulsive region where the molecules want to push each other away. They're too close. Their cores are overlapping, if you will. And at long distances, they attract each other, and with a fairly weak attraction in the vapor phase in most cases, at least at long distances. But there's an optimum distance at which their energy of interaction is at a minimum, and that's this parameter epsilon AB that characterizes the degree to which the molecules stick together. Okay, so how do we get epsilon AB? Well, this depends on the identities of the A and the B molecules, but fortunately we have a rather simple way of estimating how strong two molecules of different types will attract each other, and that is by thinking about how strongly pairs of the same type interact with each other, right? So I can think about the interaction between a BB collision pair and the interaction between an AA collision pair, and I can use the epsilon AA and the epsilon BB to estimate the epsilon AB, and these are just these so-called Lorentz-Berthelot mixing rules for describing the effective potentials between mixtures. So we won't go into that. Maybe you should see Jacob's book if you want to see more about that. But here is the formula for the interaction. It is a geometric mean of the interactions between the pure gases, and we again have the sigma AB term here with the arithmetic mean of the two diameters. This is again a harmonic mean that gives you the effective molecular masses of the collision pair. So every mean that you can imagine here is represented, and at the end of the day, the formula that Chapman and Enskog derived is this. The diffusivity of AB, again, has the T to the 3/2 dependence, again, has the effective mass to the -1/2, again, pressure to the -1, and again, collision diameter to the power 2, to the power -2. There is this collision integral that characterizes the degree to which they stick. And that depends on this kT over epsilon parameter. So when you look up this kT over epsilon, you get the value of this collision parameter, and we'll continue more next time.